Back in 2013, a paper from Google completely changed how computers understand language. And the breakthrough wasn't some new, hyper-complex model. Actually, it was the exact opposite, radical simplicity. By solving a huge efficiency problem, researchers stumbled upon something incredible, the hidden geometry of meaning itself.
Okay, let's start with a classic puzzle. King is to queen as man is to... The answer, of course, is woman. But here's the wild part. A computer can solve this, not by using logic or reasoning, but by doing incredibly simple math. And by the end of this, you'll see exactly how the vector for king minus man plus woman mathematically points directly to queen.
To really get why this was such a revolution, we first have to understand the massive wall that language AI researchers were up against. See, before 2013, computers treated words as completely separate, isolated things.
They called them atomic units, and what that means is, in the computer's mind, the word kitten was just as different from cat as the word car was. There was zero built-in understanding that a kitten is just a young cat. Every single one of those relationships had to be learned from scratch, which, as you can imagine, was just brutally inefficient.
Now, it's not like people weren't trying to solve this. There were early neural networks like NLMs that could learn these relationships. They were powerful, for sure, but man, were they slow. They hit a computational brick wall. Trying to train them on the billions of words from the internet that you need for real understanding, it was basically impossible. Just not practical.
And here's the technical reason why. The problem was all in the math. If you look at these formulas, the real killer is the letter H, which stands for the hidden layer. Those terms I've highlighted, where you're multiplying everything by H, that was the bottleneck. This one layer was doing so much computational heavy lifting that scaling it up to billions of words was just off the table.
So how do you get past a wall like that? Well, the genius here wasn't to build something even more complicated. The solution was the complete opposite. It came from a moment of profound, radical simplification.
The observation was brilliant. The researchers basically looked at that expensive hidden layer, the H, that was causing all the trouble, and asked, what if we just get rid of it? Seriously. They proposed using much simpler models that didn't have that layer at all. It was a huge bet. They were gambling that what they lost in model complexity, they could more than make up for with the sheer volume of data they could now process.
And this bet led to two new, really elegant architectures. The first is called CBO, or Continuous Bag of Words. You can think of it like a fill-in-the-blank game. It looks at the words around a blank space and tries to predict the missing word. The second, Skipgram, does the complete opposite. It takes a single word and tries to predict the words that are likely to be around it. Just two simple, inverted ways of looking at the same problem.
And here is the payoff. That expensive H term from before, it's just gone. It's been replaced by a much cheaper term that scales with the logarithm of the vocabulary size. Now, you don't need to be a mathematician to get this. All it means is that even if your vocabulary has millions of words, the computation is still totally manageable. This wasn't a small speed-up. It was a fundamental shift that made the impossible possible.
This massive leap in efficiency led to something truly remarkable. By being able to process billions of words, these simple models started to uncover a hidden structure in our language. They found that meaning could be mapped, that our words actually have a kind of geometry.
This sentence right here was the mic drop moment of the whole paper. It proved that abstract concepts like gender or royalty could be captured and manipulated with simple arithmetic. Think of it like a map. The idea of royalty wasn't programmed in. It just emerged as a specific direction, like north, in the vast space of word meanings.
Let's walk through another one. Big is to biggest, as small is to what? Well, you start with the vector for biggest, then you subtract the vector for big. What's left is the pure mathematical concept of superlative. You then just add that concept to the vector for small. The model then scans its entire vocabulary for the closest word, and it lands on smallest. It's just beautiful.
Now, this all sounds really cool, but you might be wondering if it's just a neat party trick. And the answer is a definitive no. The new, simpler models were not only way faster, but the data showed they were also significantly more accurate. Let's look at the numbers.
So check this out. On a dataset of 6 billion words, the new Skipgram model hit over 65% accuracy, way better than the old model. And it did this while using vectors with 10 times more detail. But the real kicker? The training time. Just 2.5 days. The old model would have taken months to do the same job, and it would have gotten a worse result. It's not even a fair fight.
And if you're a visual person, this bar chart tells the whole story. That bar on the left, that's the old, complex model. And the two much bigger bars on the right, those are the new, simple ones. The leap in performance is just undeniable. It's a crystal clear victory for efficiency and scale.
So let's zoom out. What's the core principle that this work unlocked? Because it wasn't about more than just building a better model. It was a fundamental discovery about language itself.
The principle is this. Relationships between words act like simple directions on a compass. The concept of going from singular to plural, like dog to dogs, is one consistent direction. The concept of a capital city, linking France to Paris, is another. It turns out that meaning isn't some fuzzy, abstract idea. It actually has a mappable geometric structure.
And the model found these relationships all over the place. Paris minus France plus Italy gives you Rome. Okay, that makes sense. But what about Einstein minus scientist plus Messi gives you midfielder? Or Microsoft minus Windows plus Google gives you Android? The most amazing part is that no one programmed these rules in. The model learned all of it just by reading text.
And that brings us back to this number, 6 billion. This number is really the hero of the story. Without the insane efficiency of the new models, training on a dataset this huge was a complete pipe dream. And it was that massive scale that allowed all of these subtle mathematical patterns in language to finally emerge from the noise. Efficiency enabled scale, and scale enabled discovery.
Which leaves us with a final provocative thought. This breakthrough proved that something as messy and human as language has a concrete mathematical structure hiding underneath. So it raises a profound question that we're still exploring today. If the relationships between words can be mapped out like this, what other complex concepts are just waiting for us to chart their geometry?